The following program is brought to you by Caltech.
Welcome back. Last time, we introduced the learning problem. And if you have an application in your domain that you wonder if machine learning is the right technique for it, we found that there are 3 criteria that you should check. You should ask yourself, is there a pattern to begin with that we can learn? And we realized that this condition can be intuitively met in many applications, even if we don't know mathematically what the pattern is. The example we gave was the credit card approval. There is clearly a pattern if someone has a particular salary, has been in residence for so long, has that much debt, and so on, that this is somewhat correlated to their credit behavior. And therefore, we know that a pattern exists, in spite of the fact that we don't know exactly what the pattern is. The second item is that we cannot pin down the pattern mathematically, like the example I just gave, and this is why we resort to machine learning. The third one is that we have data that represents that pattern. In the case of the credit application, for example, there are historical records of previous customers, and we have the data they wrote in their application when they applied, and we have some years' worth of record of their credit behavior. So we have data that are going to enable us to correlate what they wrote on the application to their eventual credit behavior, and that is what we are going to learn from. Now, if you look at the 3 criteria, basically there are 2 that you can do without and 1 that is absolutely essential. Okay, so what do I mean? Let's say that you don't have a pattern. Okay, well, if you don't have a pattern, then you can try learning, and the only problem is that you will fail. Okay, that doesn't look sound very encouraging, but the idea here is that when we develop the theory of learning, we will realize that you can apply the technique regardless of whether there is a pattern or not, and you are going to determine whether there is a pattern or not. So you are not going to be fooled and think, I learned, and then give the system to your customer, and the customer will be disappointed. There is something you can actually measure that will tell you whether you learned or not. So if there is no pattern, there is no harm done in trying machine learning. The other one also, you can do without. Let's say that we can pin the thing down mathematically. Okay? Well, in that case, machine learning is not the recommended technique. It will still work. It may not be the optimal technique. If you can outright program it and find the result perfectly, then why bother, generate examples and try to learn and go through all of that? But machine learning is not going to refuse. It is going to learn, and it's going to give you a system. May not be the best system in this case, but it's a system nonetheless. The third one, I'm afraid you cannot do without. You have to have data. Machine learning is about learning from data. And if you don't have data, there is absolutely nothing you can do. Okay? So this is basically the picture about the context of machine learning. Now, we went on to focus on one type, which is supervised learning. And in the case of supervised learning, we have a target function. The target function we are going to call f, that is our standard notation. And this corresponds, for example, to the credit application. X is your application, and f of x is whether you are a good credit risk or not for the bank. So if you look at the target function, the main criteria about the target function is that it's unknown. This is a property that we are going to insist on, and obviously unknown is a very generous assumption, which means that you don't have to worry about what pattern you are trying to learn. It could be anything, and you will learn it, if we manage to do that. There is still a question mark about that. But it's a good assumption to have, or lack of assumption, if you will, because then you know that you don't worry about the environment that generated the examples. You only worry about the system that you use to implement machine learning. Now, you are going to be given data, and the reason it's called supervised learning is that you are not only given the input x's, as you can see here, you are also given the output, the target outputs. So in spite of the fact that the target function is generally unknown, it is known on the data that I give you. This is the data that you are going to use as training examples, and that you are going to use to figure out what the target function is. So in the case of supervised learning, you have the targets explicitly. In the other cases, you have less information than the target, and we talked about it, like unsupervised learning, where you don't have anything, and reinforcement learning, where you have partial information, which is just a reward or punishment for a choice of a value of y that may or may not be the target. Finally, you have the solution tools. These are the things they are going to choose in order to solve the problem, and they are called the learning model, as we discussed. They are the learning algorithm and the hypothesis set. And the learning algorithm will produce a hypothesis, the final hypothesis, the one that you are going to give to your customer. And we give the symbol G for that. And hopefully G approximates F, the actual target function, which remains unknown. And G is picked from a hypothesis set. And the general symbol for a member of the hypothesis set is small h. So small h is a generic hypothesis. The one you happen to pick, you are going to call G. Okay? Now we looked at an example of a learning algorithm. So first, the learning model, the perceptron itself, which is a linear function thresholded, that happens to be the hypothesis set. And then there is an algorithm that goes with it that chooses which hypothesis to report based on the data. And the hypothesis in this case is represented by the purple line. Different hypotheses in the set script H will result in different lines. Some of them are good and some of them are bad in terms of separating correctly the examples, which are the pluses and the minuses. And we found that there's a very simple rule to adjust the current hypothesis while the algorithm is still running in order to get a better hypothesis. And once you have all the points classified correctly, which is guaranteed in the case of the perceptron learning algorithm if the data was linearly separable in the first place, then you will get there, and that will be the G that you are going to report. Okay? Now, we ended the lecture on a sort of a sad note, because after all of this encouragement about learning, we asked ourselves, well, can we actually learn? Okay? So we said, okay, it's unknown function. Unknown function is an attractive assumption, as I said. But can we learn an unknown function really? And then we realized that if you look at it, okay, it's really impossible. Why is it impossible? Because I am going to give you a finite data set, and I'm going to give you the value of the function on this set. Good. Now I'm going to ask you, what is the function outside that set? How in the world are you going to tell what the function is outside if the function is genuinely unknown? Couldn't it assume any value it wants? Yes, it can. I can give you 1,000 points, 1,000,000 points, and on the 1,000,001st point, still the function can behave any way it wants. So it doesn't look like the statement we made is feasible in terms of learning. And therefore, we have to do something about it. And what we are going to do about it is the subject of this lecture. Okay. Now, the lecture is called Is Learning Feasible? And I am going to address this question in extreme detail from beginning to end. This is the only topic for this lecture. Okay. Now, if you want an outline, it's really a logical flow. But if you want to cluster it into points, we are going to start with a probabilistic situation that is a very simple probabilistic situation, doesn't seem to relate to learning, but it will capture the idea, can we say something outside the sample data that we have? So we are going to answer it in a way that is concrete and where the mathematics is very friendly. And then after that, I'm going to be able to relate that probabilistic situation to learning as we stated. It will take two stages. First, I will just sort of translate the expressions into something that relates to learning, and then we will move forward and make it correspond to real learning. And that's the last one. And then after we do that and we think we are done, we find that there is a serious dilemma that we have, and we will find a solution to that dilemma and then declare victory that indeed learning is feasible in a very particular sense. Okay, so let's start with the experiment that I talked about. Consider the following situation. You have a bin, and the bin has marbles. The marbles are either red or green. Okay, that's what it looks like. And we are going to do an experiment with this bin. And the experiment is to pick a sample from the bin, some marbles. So let's formalize what the probability distribution is. There is a probability of picking a red marble, and let's call it mu. Okay? So now you think of mu as the probability of a red marble. Now, the bin is really just a visual aid to make us relate to the experiment. You can think of this abstractly as a binary experiment. Two outcomes, red or green. Probability of red is mu independently from one point to another. If you want to stick to the bin, you can say the bin has an infinite number of marbles, and the fraction of red marbles is mu, or maybe it has finite number of marbles, and you are going to pick the marbles but replace them. Okay? But the idea now is that every time you reach in the bin, the probability of picking a red marble is mu. That's the rule. Okay? Now, there is a probability of picking a green marble, and what might that be? Okay? That must be 1 minus mu. Okay? So that's the setup. Now, the value of mu is unknown to us. So in spite of the fact that you can look at this particular bin and see, okay, there is less red than green, so mu must be small and all of that, you don't have that advantage in real. The bin is opaque, it's sitting there, and I reach for it like this. Okay? So now that I declare mu is unknown, you probably see where this is going. Okay? Unknown is a famous word from last lecture, and that will be the link to what we have. Okay. Now, we pick n marbles independently, capital N, and I'm using the same notation for capital N, which is the number of data points in learning, deliberately. Okay? So the sample will look like this, and it will have some red and some green. It's a probabilistic situation. And we are going to call the fraction of marbles in the sample. Okay? So this now is a probabilistic quantity. Mu is an unknown constant sitting there. If you pick a sample, someone else picks a sample, you will have a different frequency in sample from the other person, and we are going to call it nu. Now, interestingly enough, nu also should appear in the figure. So it says nu equals fraction of red marbles. So that's where it lies. Okay? Here is a nu. For some reason that I don't understand, the app wouldn't show nu in the figures. Okay? So I decided maybe the app is actually a machine learning expert. It doesn't like things in sample. It only likes things that are real. So it knows that nu is not important. It's not an indication. We are really interested in knowing what's outside. So it kept the mu, but actually deleted the nu. At least that's what we are going to believe for the rest of the lecture. Okay? Now, this is the bin. So now the next step is to ask ourselves the question we asked in machine learning. Does nu, which is the sample frequency, tell us anything about mu, which is the actual frequency in the bin that we are interested in knowing? Okay? The short answer, this is to remind you what it is. The short answer is no. Why? Because the sample can be mostly green, while the bin is mostly red. Anybody doubts that? The thing could have, 90% red, and I pick 100 marbles, and all of them happen to be green. This is possible, correct? So if I ask you what is actually mu, you really don't know from the sample. You don't know anything about the marbles you did not pick. Okay? Well, that's the short answer. The long answer is yes. Okay? Not because no and yes, okay, but just this is more elaborate. We have to really discuss a lot in order to get there. Okay, so why is it yes? Because if you know a little bit about probability, you realize that if the sample is big enough, the sample frequency, which is nu, the mysterious disappearing quantity here, that is likely to be close to mu. Okay? Think of a presidential poll. Okay? There are maybe 100 million or more voters in the US, and you make a poll of 3,000 people. You have 3,000 marbles, so to speak. And you look at the result in the marbles, and you tell me how the 100 million will vote. How the heck did you know that? Okay? So now the statistics come in. That's where the probability plays a role. And the main distinction between the two answers is possible versus probable. In science and in engineering, you go a huge distance by settling for not absolutely certain, but almost certain. It opens a world of possibilities. And this is one of the possibilities that it opens. Okay. So now we know that from a probabilistic point of view, nu does tell me something about mu. The sample frequency tells me something about the bin. So what does it exactly say? So now we go into a mathematical formulation. Okay. Well, in words, it says in a big sample, nu, the sample frequency, should be close to mu, the bin frequency. Okay? So now the symbols that go with that. What is a big sample? Large n, our parameter n. Okay? And how do we say that nu is close to mu? We say that they are within epsilon. Okay? That is our criteria. So now with this in mind, we are going to formalize this. Okay? Now, the formula that I'm going to show you is a formula that is going to stay with us for the rest of the course. I would like you to pay attention, and I'm going to build it gradually. We are going to say that the probability of something is small. Okay? So we're going to say that it's less than or equal to, and hopefully the right-hand side will be a small quantity. Now, if I'm claiming that the probability of something is small, it must be that that thing is a bad event. I don't want it to happen. So we'll have a probability of something bad happening being small. Okay? What is a bad event in the context we are talking about? It is that nu does not approximate mu well. They are not within epsilon of each other. And if you look at it, here you have nu minus mu in absolute value, so that's the difference in absolute value. That happens to be bigger than epsilon. So that's bad, because that tells us that they are further away from our tolerance epsilon. We don't want that to happen. And we would like the probability of that happening to be as small as possible. Well, how small can we guarantee it? Good news, okay? It's e to the minus n. It's a negative exponential. That is great because negative exponentials tend to die very fast. So if you get a bigger sample, this will be diminishingly small probability. So the probability of something bad happens will be very small, and we can claim that indeed nu will be within epsilon from mu, and we will be wrong for a very minute amount of the time. But that's the good news, okay? Now the bad news. Ouch. Epsilon is our tolerance, okay? If you are a very tolerant person, you say, okay, I just want nu and mu to be within, let's say, 0.1. Okay? That's not very much to ask. Now, the price you pay for that is that you plug in the exponent, not epsilon, but epsilon squared. So that becomes 0.01. 0.01 will dampen n significantly, and you lose a lot of the benefit of the negative exponential. And if you are more stringent and you say, okay, I really want nu to be close to mu. I am not fooling around here, okay? So I'm going to pick epsilon to be 10 to the minus 6. Good for you. 10 to the minus 6, pay the price for it. You go here, and now that's 10 to the minus 12. That will completely kill any n you will ever encounter. So the exponent now will be around 0. So this probability will be around 1, if that was the final answer. That's not yet the final answer. So now you know that the probability is less than or equal to 1. Congratulations. You knew that already. Okay? Well, this is almost the formula, but it's not quite. What we need is fairly trivial. We just put 2 here and 2 there. Okay? Now, between you and me, I prefer the original formula better, without the 2's. Okay? However, the formula with the 2's has a distinct advantage of being true. Okay? So we have to settle for that. Okay? Now, that inequality is called Hoeffding's inequality. It is the main inequality we are going to be using in the course. You can look for the proof. It's a basic proof in mathematics. It's not that difficult, but definitely not trivial. And we are going to use it all the way, and this is the same formula that will get us to prove something about the VC dimension. If the buzzword VC dimension means anything to you, it will come from this after a lot of derivation. Okay? So this is the building blocks that you have to really know cold. Okay? So now, if you want to translate the Hoeffding inequality into words, what we have been talking about is that we would like to make the statement mu equals nu. That will be the ultimate. You look at the in-sample frequency, that's the out-of-sample frequency. That's the real frequency out there, okay? But that's not the case, okay? So we actually are making the statement mu equal nu, but we are not making the statement, we are making a PAC statement. And that stands for, this statement is probably, approximately correct. Okay? Probably because of this. This is small, so the probability of violation is small. Approximately because of this. We are not saying that mu equals nu, we are saying that they are close to each other. Okay? And that theme will remain with us in learning. Okay. So we put the glorified Hoeffding's inequality at the top, and we spend a view graph analyzing what it means. In case you forgot what nu and mu are, I put the figure. So mu is the frequency within the bin. This is the unknown quantity that we want to tell. And nu is the disappearing quantity, which happens to be the frequency in the sample you have. Okay. So what about the Hoeffding inequality? Well, the one attraction of this inequality is that it is valid for every n positive integer and every epsilon which is greater than 0. Pick any tolerance you want, and for any number of examples you want, this is true. It's not an asymptotic result, it's the result that holds for every n and epsilon. That's a very attractive proposition for something that has an exponential in it. Okay? Now, Hoeffding inequality belongs to a large class of mathematical laws, which are called the laws of large numbers. Okay? So this is one law of large numbers, one form of it, and there are tons of them. Okay? This happens to be one of the friendliest because it's not asymptotic and happens to have an exponential in it. Okay? Now, one observation here is that if you look at the left-hand side, we are computing this probability. This probability patently depends on mu. Mu appears explicitly in it, and also mu affects the probability distribution of nu. Nu is the sample in n marbles you picked. That's a very simple binomial distribution. You can find the probability that nu equals anything based on the value of mu. So the probability that this quantity, which depends on mu, exceeds epsilon, the probability itself does depend on mu. However, we are not interested in the exact probability. We just want to bound it. And in this case, we are bounding it uniformly. As you see, the right-hand side does not have mu in it. And that gives us a great tool, because now we don't use the quantity that we already declared is unknown. Mu is unknown. It will be a sort of a vicious argument if I go and say that it depends on mu, but I don't know what mu is. Now you know uniformly, regardless of the value of mu, mu could be anything between 0 and 1, and this will still be bounding the deviation of the sample frequency from the real frequency. Okay? That's a good advantage. Now, the other point is that there is a trade-off that you can read off the inequality. What is the trade-off? The trade-off is between n and epsilon. Okay. In the typical situation, if we think of n as the number of examples that are given to you, the amount of data, in this case, the number of marbles out of the bin, okay? N is usually dictated. Someone comes and gives you a certain resource of examples. Okay? Epsilon is your taste in tolerance. You are very tolerant, you pick epsilon equals 0.5, okay? That would be very easy to satisfy, okay? And if you are very stringent, you can pick epsilon smaller and smaller. Now, because they get multiplied here, okay, the smaller the epsilon is, the bigger the n you need in order to compensate for it and come up with the same level of probability bound. Okay? And that makes a lot of sense. Okay? If you have more examples, you are more sure that nu and mu will be close together, even closer and closer and closer as you get larger n. So this makes sense. Okay? Finally, it's a subtle point, but it's worth saying. Well, we are making the statement that nu is approximately the same as mu, okay? And this implies that mu is approximately the same as nu. What is this? The logic here is a little bit subtle. Obviously, I mean, the statement is a tautology, but I'm just making a logical point here. When you run the experiment, you don't know what mu is. Mu is an unknown. It's a constant, okay? The only random fellow in this entire operation is nu. That is what the probability is with respect to. You generate different samples, and you compute the probability. This is the probabilistic thing. This is a happy constant sitting there, albeit unknown, okay? Now, the way you are using the inequality is to infer mu, the sample here, from nu. That is not the cause and effect that actually takes place. The cause and effect is that mu affects nu, not the other way around. But we are using it the other way around, okay? Lucky for us, the form of the probability is symmetric. Therefore, instead of saying that nu tends to be close to mu, which will be the accurate logical statement, mu is there, and nu has a tendency to be close to it. We, instead of that, say that, okay, I know already nu, and now mu tends to be close to nu. That's the logic we are using. Okay? Okay. Now, I think we understand what the bin situation is, and we know what the mathematical condition that corresponds to it is. What I'd like to do, I'd like to connect that to the learning problem we have. Okay, so in the case of a bin, the unknown quantity that we want to decipher is a number, mu, just unknown. What is the frequency inside the bin? In the learning situation that we had, the unknown quantity we would like to decipher is a full-fledged function. It has a domain x that could be at 10th order Euclidean space. Y could be anything, could be binary like the perceptron, could be something else. That's a huge amount of information. The bin has only one number. This one, if you want to specify, that's a lot of specification. Okay? So how am I going to be able to relate the learning problem to something that simplistic? Okay, so the way we are going to do it is the following. Think of the bin as your input space in the learning problem. That's the correspondence. So every marble here is a point X. That is a credit card applicant. Okay? So if you look closely at the gray thing, you will read salary, years in residence, and whatnot. Okay? You can see it here because it's too small. Okay? Now, the bin has all the points in the space. Therefore, this is really the space. Okay? That's the correspondence in our mind. Now we would like to give colors to the marbles. Okay? So here are the colors. There are green marbles, and they correspond to something in the learning problem. What do they correspond to? They correspond to your hypothesis getting it right. So what does that mean? There is a target function sitting there, right? You have a hypothesis. The hypothesis is a full function, like the target function is. You can compare the hypothesis to the target function on every point. Okay? And they either agree or disagree. If they agree, please color the corresponding point in the input space, color it green. Okay? Now, I'm not saying that you know which ones are green and which ones are not, because you don't know the target function overall. I'm just telling you the mapping that takes an unknown target function into an unknown mu. So both of them are unknown, admittedly, but that's the correspondence that maps it. And now you go, and there are some red ones, and you guessed it. You color the thing red if your hypothesis got the answer wrong. So now I am collapsing the entire thing into just agreement, disagreement between your hypothesis and the target function. And that's how you get to color the bin. Because of that, you have a mapping for every point, whether it's green or red, according to this rule. Now, this will add a component to the learning problem that we did not have before. okay? There is a probability associated with the bin. There is a probability of picking a marble and independently and all of that, okay? When we talked about the learning problem, there was no probability. I will just give you a sample set, and that's what you work with. So let's see what is the addition we need to do in order to adjust the statement of the learning problem to accommodate the new ingredient. And the new ingredient is important because otherwise we cannot learn. It's not like we have the luxury of doing without it. So we go back to the learning diagram from last time. Do you remember this one? Let me remind you. Okay. Here is your target function, and it's unknown. And I promised you last time that it will remain unknown, and the promise will be fulfilled. We are not going to touch this box. We are just going to add another box to accommodate the probability. Okay? And the target function generates the training example. These are the only things that the learning algorithm sees. It picks a hypothesis from the hypothesis set and produces it as the final hypothesis, which hopefully approximates F. That's the game. So what is the addition we are going to do? In the bin analogy, this is the input space. Now the input space has a probability. So I need to apply this probability to the points from the input space that are being generated. Okay? So I am going to introduce a probability distribution over the input space. So now the points in the input space, let's say the d-dimensional Euclidean space, are not just generic points now. There is a probability of picking one point versus the other. And that is captured by the probability which I am going to call capital P. Now the interesting thing is that I am making no assumptions about P. P can be anything. I just sort of want a probability. Okay? So invoke any probability you want, and I am ready with the machinery. So I am not going to restrict the probability distributions over X. That's number one. So this is not as bad as it looks. Number two, I don't even need to know what P is. Of course, the probability choice will affect the choice of the probability of getting a green marble or a red marble, because now the probability of different marbles changed. So it could change the value mu. But the good news with the Höfding is that I could bound the performance independently of mu. So I can get away with not only any P, but with a P that I don't know. And I will still be able to make the mathematical statement. So this is a very benign addition to the problem. And it will give us very high dividends, which is the feasibility of learning. So what do you do with the probability? You use the probability to generate the points x1 up to xn. So now x1 up to xn are assumed to be generated by that probability independently. That's the only assumption that is made. If you make that assumptions, we are in business. Okay? But the good news, as I mentioned before, we did not compromise about the target function. You don't need to make assumptions about the function you don't know and you want to learn, which is good news. And the addition is almost technical. That, okay, there is a probability somewhere generating the points. If I know that, then I can make a statement in probability. Obviously, you can make that statement only to the extent that the assumption is valid. And we can discuss that in later lectures when the assumption is not valid. Okay. So, okay, happy ending. We are done, and we now have the correspondence. Are we done? Well, not quite. Okay, why are we not done? Because the analogy I gave you requires a particular hypothesis in mind. I told you that the red and green marbles correspond to the agreement between H and the target function. So when you tell me what H is, you dictate the colors here, right? All of these colors. This is green, not because it's inherently green, not because of anything inherent about the target function. It's because of the agreement between the target function and your hypothesis H. Okay? That's fine. But what is the problem? Well, the problem is that I know that for this H, nu generalizes to mu. You're probably saying in your mind, yeah, but H could be anything. I don't see the problem yet. Okay? Now, here is the problem. What we have actually discussed is not learning, it's verification. The situation as I describe it, you have a single bin and you have red and green marbles and this and that corresponds to the following. A bank comes to my office, we would like a formula for credit approval. Okay? And we have data. So instead of actually taking the data and searching hypotheses and picking one that, like the perceptual learning algorithm, here is what I do that corresponds to what I just described. Okay, you guys want a linear formula? Okay, I guess the salary should have a big weight, let's say 2. The outstanding debt is negative, so that should be weight minus 0.5. And years in residence, okay, are important, but not that important, so let's give them a 0.1. And let's pick a threshold that is high in order for you not to lose money. Let's pick a threshold of 0.5. Sitting down, improvising an age. Okay? Now, after I fix the age, I ask you for the data and just verify whether the age I picked is good or bad. That I can do with the bin, because I'm going to look at the data. If I miraculously agree with everything in your data, I can definitely declare victory by Höfting. But what are the chances that this will happen in the first place? I have no control over whether I will be good in the data or not. The whole idea of learning is that I am searching the space to deliberately find a hypothesis that works well on the data. In this case, I just dictated a hypothesis, and I was able to tell you for sure what happens out of sample. But I have no control of what the news I'm going to tell you. You can come to my office, I improvise this, I go to the data, and I tell you I have a fantastic system. It generalizes perfectly, and it does a terrible job. That's what I have, because when I tested it, new was terrible. So that's not what we are looking for. What we are looking for is to make it learning. So how do we do that? So no guarantee that new will be small, and we need to choose H from choose the hypothesis from multiple H's. That's the game. And in that case, you are going to go for the sample, so to speak, generated by every hypothesis, and then you pick the hypothesis that is most favorable, that gives you the least error. Okay? So now, okay, that doesn't look like a difficult thing. It worked with one bin. Maybe I can have more than one bin to accommodate the situation where I have more than one hypothesis. Looks plausible. Okay? So let's do that. We will just take multiple bins. Okay? So here is the first bin. Okay? Now you can see that this is a bad bin, so that hypothesis is terrible. Okay? And the sample reflects that to some extent. Okay? But we are going to have other bins. So let's call this something. So this bin corresponds to a particular H. And since we are going to have other hypotheses, we are going to call this H1 in preparation for the next guy. The next guy comes in, and you have H2. And you have another mu2. This one looks like a good hypothesis, and it's also reflected in the sample. And it's important to look at the correspondence. Okay? If you look at the top red point here and the top green point here, this is the same point in the input space. It just was colored red here and colored green here. Why did that happen? Because the target function disagrees with this H, and the target function happens to agree with this H. That's what got the color green. And when you pick a sample, the sample also will have different colors because the colors depend on which hypothesis, and these are different hypotheses. Okay? That looks simple enough. So let's continue. And we can have M of them. Okay? I am going to consider a finite number of hypotheses just to make the math easy for this lecture. And we're going to go more sophisticated when we get into the theory of generalization. Okay, so now I have this. This is good. Now I have samples, and the samples are here different. And I can do the learning. And the learning now abstractly is to scan these samples, looking for a good sample. And when you find a good sample, you declare victory because of Höfting, and you say that it must be that the corresponding bin is good, and the corresponding bin happens to be the hypothesis you chose. So that is an abstraction of learning. Okay? That was easy enough. Now, because this is going to stay with us, I'm now going to introduce the notation that will survive with us for the entire discussion of learning. Okay? So here is the notation. Now, we realize that both the mu, which happens to be inside the bin, and nu, which happens to be the sample frequency, in this case the sample frequency of error, both of them depend on H. So I'd like to give a notation that makes that explicit. So the first thing, I'm going to call mu and nu with a descriptive name. So nu, which is the frequency in the sample you have, is in sample. That is the standard definition for what happens in the data that I give you. If you perform well in sample, it means that your error in the sample that I give you is small. Okay? And because it is called in sample, we are going to denote it by E in. Okay? I think this is worth blowing up because it's an important one. Okay? So this is our standard notation for the error that you have in sample. Okay? Now we go and get the other one, which happens to be mu, and that is called out of sample. Okay? So if you are in this field, you guess what matters is the out of sample performance. That's the lesson. Out of sample means something that you haven't seen. And if you perform out of sample on something that you haven't seen, then you must have really learned. So that's the standard for it, and the name for it is E out. Okay? Okay, so with this in mind, we realize that we don't yet have the dependency on H, which we need. Okay? So we are going to make the notation a little bit more elaborate by calling E in and E out, calling them E in of H and E out of H. Why is that? Well, the in-sample performance, you are trying to see the error of approximating the target function by your hypothesis. That's what E in is. So obviously it depends on your hypothesis. So it's E in of H. Someone else picks another H, they will get another E in of H of their H. Okay? Similarly, E out, the corresponding one, is E out of H. Okay? So now what used to be nu is now E in of H. What used to be mu inside the bin is E out of H. Okay? Now the Hoeffding inequality, which we know all too well by now, said that. So all I'm going to do is just replace the notation. And now it looks a little bit more crowded, but it's exactly the same thing. Okay? The probability that your in-sample performance deviates from your out-of-sample performance by more than your prescribed tolerance is less than or equal to a number that is hopefully small. Okay? And you can go back and forth. There's a new mu, or you can go here and you get the new notation. Okay? So we are settled on the notation now. Now let's go for the multiple bins and use this notation. Okay. So these are the multiple bins as we left them. We have the hypothesis H1 up to Hm, and we have the mu1 and mu_n. And if you see 1 to m, again, this is a disappearing nu, the symbol that the app doesn't like. Okay? But thank God we switched notation so that something will appear. Okay? Yeah, okay. So right now, that's what we have. Every bin has an out-of-sample performance, and out-of-sample is out of sample. Okay? Okay, so this is the sample. What's in it is in sample. What is not in it is out of sample. And the out of sample depends on H1 here, H2 here, and Hm here. And obviously, these quantities will be different according to the sample, and these quantities will be different according to the ultimate performance of your hypothesis. Okay? Okay, so we solved the problem. It's not verification. It's not a single bin. It's real learning. I'm going to scan these. So that's pretty good. Are we done already? Not so fast. Okay, what's wrong? Okay, let me tell you what's wrong. The Hoeffding inequality that we have happily studied and declared important and all of that doesn't apply to multiple bins. What? Okay. You told us mathematics and you go read the proof and all of that, and what, are you just pulling tricks on us? What is the deal here? Okay. And you even can complain. We sat for like what, 40 minutes now, going from a single bin, mapping it to the learning diagram, mapping it to multiple bins, and now you tell us that the main tool we developed doesn't apply. Why doesn't apply? Why doesn't it apply? And what can we do about it? Okay. Let me start by saying why it doesn't apply, and then we can go for what we can do about it. Okay. Now, everybody has a coin. I hope the online audience have a coin ready. I'd like to ask you to take the coin out and flip it, let's say, 5 times. and record what happens. Okay? And when you are at home, flip the coin 5 times. Please, if you happen to get all 5 heads in your experiment, then text us that you got all 5 heads. If you get anything else, don't bother text us. Okay? We just want to know if someone will get 5 heads. Okay? Everybody's done flipping the coin? Okay? Because you have been so generous and cooperative, you can keep the coin. Okay? Okay, now, did anybody get 5 heads? All 5 heads? Okay. Congratulations, sir. You have a biased coin, right? We just argued that in sample corresponds to out of sample, and we have this Höfding thing, and therefore, if you get 5 heads, it must be that this coin gives you heads. Okay? We know better. So in the online audience, what happened?
Yeah, in the online audience, it's also 5 heads.
There are lots of biased coins out there. Okay? Are there really biased coins? Okay? No. What is the deal here? So let's look at here. Here I can, with the audience here, I didn't want to push my luck with 10 coins because it's a live broadcast. So I said 5 will work, okay? For the analytical example, let's take 10 coins, okay? Let's say you have a fair coin, which every coin is, okay? You have a fair coin, and you toss it 10 times. What is the probability that you will get all 10 heads? Pretty easy, 1/2 times 1/2, 10 times, and that will give you about 1 in 1,000. No chance that you will get it, okay? Okay, no chance, but very little chance. Okay, now the second question is the one we actually ran the experiment for. If you toss 1,000 fair coins, it wasn't 1,000 here, it's how many there, maybe out there is 1,000, okay? What is the probability that some coin will give you all 10 heads? Not difficult at all to compute. And when you get the answer will be, it's actually more likely than not. Okay? So now, it means that the 10 heads in this case are no indication at all of the real probability. That is the game we are playing. Can I look at the sample and infer something about the real probability? No. In this case, you will get 10 heads, and the coin is fair. Why did this happen? This happened because you try too hard. Eventually, what will happen is, okay, Höfding applies to any one of them, okay? So, but there is a probability, let's say, 0.5% that you'll be off here. Another 0.5% that you'll be off here. If you do it often enough, and you are lucky enough that the 0.5% are disjoint, you will end up with extremely high probabilities that something bad will happen somewhere. That's the key. So let's translate this into the learning situation. So here are your coins, okay? And how do they correspond to the bins? Well, it's a binary experiment, whether you are picking a red marble or a green marble, or you are flipping a coin getting heads or tails. It's a binary situation, so there is a direct correspondence. Just get the probability of heads being mu, which is the probability of a red marble corresponding to them. So because the coins are fair, actually all the bins in this case are half red, half green, okay? That's really bad news for a hypothesis. The hypothesis is completely random. Half the time it agrees with the target function, half the time it disagrees. No information at all, okay? Now you apply the learning paradigm we mentioned, and you say, okay, let me generate a sample from the first hypothesis. I get this, I look at it, and I don't like that. It has some reds. I want really a clean hypothesis that performs perfectly, all green, okay? You move on, and okay, this one, even, I don't know, this is even worse, okay? You go on and on and on and on, and eventually, lo and behold, I have all greens. Bingo! I have the perfect hypothesis. I'm going to report this to my customer, and if my customer is in financial forecasting, we are going to beat the stock market and make a lot of money, and you start thinking about the car you are going to buy and all of that, okay? Well, is it bingo? No, it isn't. And that is the problem. So now we have to find something that makes us deal with multiple bins properly. Höfding inequality, if you have one experiment, it has a guarantee. The guarantee gets terribly diluted as you go. and we want to know exactly how the dilution goes. So here is a simple solution, okay? This is a mathematical slide. I'll do it step by step. There is absolutely nothing mysterious about it. Okay, so this is the quantity we've been talking about. This is the probability of a bad event. But in this case, you realize that I am putting G. Remember, G was our final hypothesis. So this corresponds to a process where you had a bunch of H's, and you picked one according to a criteria that happens to be an in-sample criteria, minimizing the error there. And then you report the G as the one that you chose. And you would like to make a statement that the probability for the G you chose, the in-sample error, happens to be close to the out-of-sample error. So you'd like the probability of the deviation being bigger than your tolerance to be, again, small. Okay? So all we need to do is find a Hoeffding counterpart to this, because now this fellow is loaded. It's not just a fixed hypothesis and a fixed bin. It actually corresponds to a large number of bins, and I am visiting the random samples in order to pick one. So clearly that the assumptions of Hoeffding don't apply that correspond to a single bin. Okay. So this probability is less than or equal to the probability of the following. Okay, I have M hypothesis, capital M hypothesis. H1, H2, H3, HM. That's my entire learning model. That's the hypothesis set that I have. Finite, as I said, I would assume. Okay? So if you look at what is the probability that the hypothesis you pick is bad, well, this will be less than or equal to the probability that the first hypothesis is bad, or the second hypothesis is bad, or the last hypothesis is bad. That is obvious. Okay? G is one of them. Okay? If it's bad, one of them is bad. So this is equal to that. Okay? This is called the union bound in probability. It's a very loose bound in general because it doesn't consider the overlap. Remember when I told you that, okay, the 0.5% here, 0.5% here, 0.5% here. If you are very unlucky and these are non-overlapping, they add up. The non-overlapping is the worst case assumption, and it is the assumption used by the union bound. So you get this, and the good news about this is that I have a handle on each term of them. The union bound is coming up. So I put the ors, and then I use the union bound to say that this is equal to, and simply sum the individual probabilities. Okay? So the half plus half plus half, 0.5% plus 0.5% plus 0.5%, this will be an upper bound on all of them. Probability that one of them goes wrong, probability that someone gets all heads, and I add the probability for all of you, and that makes it a respectable probability. Okay? So this one, the event here is implied. Okay? Therefore, I have the implyment because of the or, and this one because of the union bound where I have the pessimistic assumptions that I just need to add the probabilities. Now, all of this, again, I mean, we make simplistic assumptions, which is really not simplistic as in trivially restricting, but rather the opposite. We just don't want to make any assumptions that restrict the applicability of our result. So we took the worst case. This is it cannot get worse than that, right? So if you look at this, now I have good news to you, because each term here is a fixed hypothesis. I didn't choose anything. Every one of them has a hypothesis that was declared ahead of time. Every one of them is a bin. So if I look at a term by itself, Hoeffding applies to this exactly the same way it applied before. Okay? So this is a mathematical statement now. I'm not looking at the bigger experiment. I reduce the bigger experiment to a bunch of quantities. Each of them corresponds to a simple experiment that we already solved. So I can substitute for each of these by the bound that the Hoeffding gives me. Okay? So what is the bound that the Hoeffding gives me? That's the one. For every one of them, each of these guys was less than or equal to this quantity. One by one. All of them are obviously the same. Okay? So each of them is smaller than this quantity. Each of them is smaller than this quantity. So now I can be confident that the probabilities that I am interested in, which is the probability that the in-sample error is being close to the out-of-sample error, is like the closeness of them is bigger than my tolerance, the bad event, under the genuine learning scenario. You generate marbles from every bin, and you look deliberately for a sample that happens to be all green, or as green as possible, and you pick this one, and you want an assurance that whatever that might be, the corresponding bin will genuinely be good out of sample. That is what is captured by this probability. That is still bounded by something which also has the exponential in it, which is good. But it has an added factor that will be a very bothersome factor, which is, I have capital M of them. Now, this is the bad event. I'd like the probability to be small. I don't like to magnify the right-hand side, because that is the probability of something bad happening, okay? Now, with M, you realize, okay, if you use 10 hypotheses, this probability is probably tight. If you use 1,000,000 hypotheses, we probably are already in trouble. There is no guarantee, because now the 1,000,000 gets multiplied by what used to be a respectable probability, which is 1 in 100,000, and now you can make the statement that the probability that something bad happened is less than 10. Yeah, thank you very much. We have to take a graduate course to learn that, okay? So now you see what the problem is. And the problem is extremely intuitive. In the Q&A session after the last lecture, we all got through the discussion the assertion that if you have a more sophisticated model, the chances are you will memorize in sample, and you are not going to really generalize well out of sample, because you have so many parameters to work with. There are so many ways to look at that intuitively, and this is one of them. If you have a very sophisticated model, M is huge, let alone infinite. That's later to come. That's what the theory of generalization is about. Okay? But if you pick a very sophisticated example with a large M, you lose the link between the in sample and the out of sample. So you look at here. Okay, I didn't mean it this way, but let me go back just to show you what it is. At least you know it's over, so that's good. Okay, so this fellow is supposed to track this fellow. The in sample is supposed to track the out of sample. The more sophisticated the model you use, the looser that in sample will track the out of sample, because the probability of them deviating becomes bigger and bigger and bigger. And that is exactly the intuition we have. Okay? Now, surprise, the next one is for the Q&A. We will take a short break, and then we will go to the questions and answers. So we are now in the Q&A session, and if anybody wants to ask a question, they can go to the microphone and ask, and we can start with the online audience questions, if there are any.
Okay, so the first question is, so what happens when the Hebden inequality gives you something trivial, like less than 2?
Well, it means that either the resources of the examples you have, the amount of data you have, is not sufficient to guarantee any generalization, or, which is somewhat equivalent, that your tolerance is too stringent, okay? The situation is not really mysterious, okay? Let's say that you would like to take a poll for the president, okay? And let's say that you ask 5 people at random, okay? How can you interpret the result? Nothing, okay? You need a certain amount of respondents in order for the right-hand side to start becoming interesting. Other than that, it's completely trivial. It's very likely that what you have seen in sample doesn't correspond to anything out of sample.
So in the case of the perceptron, so the question is, would each set of W's be considered a new M? Okay,
so the perceptron, and as a matter of fact, every learning model of interest that we're going to encounter, the number of hypotheses, capital M, happens to be infinite. We were just talking about the right-hand side not being meaningful because it's bigger than 1. If you take an infinite hypothesis set and verbatim apply what I said, then you find that the probability is actually less than infinity. That is really, that's very important, okay? However, this is our first step. There will be another step where we deal with infinite hypothesis sets, and we are going to be able to describe them with an abstract quantity that happens to be finite, and that abstract quantity will be the one we are going to use in the counterpart for the Hebden inequality. That's why there is mathematics that needs to be done, okay? So I mean, it's obvious, obviously, that the perceptron has infinite number of hypotheses because you have a real space, and here is the hypothesis, and you can perturb this continuously as you want. So even just by doing this, you already have an infinite number of hypotheses without even exploring further.
Okay, and this is a popular one. Could you go over again in slide 6 of the implication of nu equals mu and vice versa?
6, okay. Okay, this is, it's a subtle point, and it's common between machine learning and statistics. What do you do in statistics? What is the cause and effect for a probability and a sample? The probability results in a sample. So if I know the probability, I can tell you exactly what are the likelihood that you will get one sample or another or another. Now, what you do in statistics is the reverse of that. You already have the sample, and you are trying to infer which probability gave rise to it. So you are using the effect to decide the cause rather than the other way around. Okay? So the same situation here. The bin is the cause. The frequency in the sample is the effect. Okay? I can definitely tell you what the distribution is like in the sample based on the bin. The utility in terms of learning is that I look at the sample and infer the bin. So I infer the effect, the cause based on the effect. There is absolutely sort of nothing terrible about that. I just wanted to make the point clear that when we write the Hoeffding inequality, which you can see here, we are talking about this event. You should always remember that nu is the thing that sort of plays around and causes the probability to happen, and mu is a constant. When we use it to predict that the out of sample will be the same as the in sample, we are really taking nu as fixed because it has to be, this is the in sample we got. Okay? And then we are trying to interpret what mu gave rise to it. And I'm just saying that in this case, since the statement is of the form that the difference between them, which is symmetric, is greater than epsilon, then if you look at this as saying that mu is there and I know that nu will be approximately the same, you can also flip that and you can say, okay, nu is here and I know that mu that gave rise to it must be the same. That's the whole idea. Okay? It's a logical thing rather than a mathematical thing.
Okay, another conceptual question that's rising is that so a more complicated model corresponds to a larger number of H's, and some people are asking, they thought each H was a model. So
okay, so each H is a hypothesis, a particular function. One of them you are going to pick, which is going to be called G, and this is the G that you are going to report as your best guess as an approximation for F. The model is the hypothesis that you are allowed to visit in order to choose one. So that's the hypothesis set, which is script H. So, and again, but there is an interesting point. I'm using the number of hypotheses as a measure for the complexity in the intuitive argument I gave you. Not clear at all that the pure number corresponds to the complexity. Not clear that anything that has to do with the size really is the complexity. Maybe the complexity has to do with the structure of individual hypotheses and whatnot. And that's a very interesting point, and that will be discussed at some point, the complexity of individual hypotheses versus the complexity of the model that captures all the hypotheses. This will be a topic that we will discuss much later in the course.
Okay, and some people getting ahead. So how do you pick G?
Okay, so we have one way of picking G that already was established last time, which is the perceptron learning algorithm. Okay, so your hypothesis set is H. The script H, it has a bunch of H's, which are the different lines in the plane. And you pick G by applying the PLA, the perceptron learning algorithm, playing around with this boundary according to the update rule until it classifies the inputs correctly, assuming they are linearly separable. And the one you end up with is the declared G. So G is just a matter of notation, a name for whichever one we settle on, the final hypothesis. So how you pick G depends on what algorithm you use and what model you use, what hypothesis set you use. So it depends on the learning model and obviously on the data.
Okay, this is a popular question, although, so it says, so how would you extend the equation to support an output that is a valid range of responses and not a binary response?
Okay, so it can be done. So one of the things that I mentioned here is that this fellow, the probability here is uniform, okay? Now, let's say that you are not talking about a binary experiment, okay? You can, instead of taking the frequency of error versus the probability of error, you can take the expected value of something versus the sample average of it. And they will be close to each other. And some obviously technical modification is needed to be here. And basically the law of large number, or the set of laws of large numbers from which this is one member, has a bunch of members that actually have to do with expected value and sample average rather than just the specific case of probability and sample average, which is also, I mean, if you take your function as being 1, 0, and you take the expected value, that will give you the sample as the expected, as the sample average, and the probability as the expected value. So it's not different animal. It's just a special case that is easier to handle. And in the other case, one of the things that matters is the variance of your variable. Okay, so it will affect the bound. So you can, here I'm choosing epsilon in general because the variance of this variable is very limited. You know, so, like let's say the probability is mu, so the variance is mu times 1 minus mu. It goes from a certain value to a certain value. So it can be absorbed, it's bounded above and below, and this is the reason why the right-hand side here can be uniformly done. If you have something that has variance that can be huge or small, then that will play a role in your choice of epsilon such that this will be valid. Okay? So the short answer is it can be done. There is a technical modification, and the main aspect of the technical modification that needs to be taken into consideration is the variance of the variable I'm talking about.
Okay, there's also a common confusion. So why are there multiple bins?
Okay, so the bin was only our conceptual tool to argue that learning is feasible in a probabilistic sense. When we used a single bin, we had a correspondence with a hypothesis, and it looked like we actually captured the essence of learning until we looked closer and we realized that if you restrict yourself to one bin and apply the Höfding inequality directly to it, what you are really working with, if you want to put it in learning, in terms of learning, is that my hypothesis set has only one hypothesis. And that corresponds to the bin. So now I am picking it, which that's my only choice, I don't have anything else. And all I am doing now is verifying that its in-sample performance will correspond to the out-of-sample performance, and that is guaranteed by the plain vanilla Höfding. Now, if you have actual learning, then you have more than one hypothesis. And we realize that the bin changes with the hypothesis, because whether a marble is red or green depends on whether the hypothesis agrees or disagrees with your target function. So different hypotheses will lead to different colors. Therefore, you need multiple bins to represent multiple hypotheses, which is the only situation that admits learning as we know it. That I'm going to explore the hypotheses based on their performance in sample and pick the one that performs best, perhaps in sample, and hope that it will generalize well out of sample.
Okay, another confusion is, so can you resolve the relationship between the probability and the big H? So I'm not clear exactly.
Okay, we apply so there are a bunch of components in the learning situation. So let me get the okay. So let's go for the it's a big diagram and it has lots of components. Okay, okay. So one big space or set is X. Okay, and another one is H. So if you look at here, okay, this is hypothesis set H. It's a set. Okay, fine. And also, if you look here, the target function is defined from X to Y. And in this case, X is also a set. The only invocation of probability that we needed to do in order to get the benefit of the probabilistic analysis in learning was to put a probability distribution on X. H, which is down there, is left as a fixed hypothesis set. There is no question of a probability on it. When we talk about the Bayesian approach at the last lecture, in fact, there will be a question of putting a probability distribution here in order to make the whole situation probabilistic. But that is not the approach that is followed for the entire course until we discuss that specific approach at the end. Question?
What do we do when there are many possible, say, hypotheses which will satisfy my criterion? Like in perceptron, for example, I could have several hyperplanes which could be separating the set. So how do
Correct.
Pick the best.
So usually with a pre-specified algorithm, you will end up with something. So the algorithm will choose it for you. But your remark now is that, okay, given that there are many solutions that happen to have 0 in-sample error, there is really no distinction between them in terms of the out-of-sample performance. I'm using the same hypothesis set, so capital M is the same, and the in-sample error is the same. So my prediction for the out-of-sample error will be the same. There is no distinction between them. The good news is that the learning algorithm will solve this for you because it will give you one specific that one ended with. But even within the ones that achieve 0 error, there is a method that we will talk about later on when we talk about support vector machines that prefers one particular solution as having a better chance of generalization. Not clear at all given what I said so far, but I'm just telling you sort of as an appetizer, there is something to be done in that regard.
Okay, and a question is, does the inequality hold for any G even if G is not optimal?
What about the G?
So if G, does it hold for any G, no matter how you pick G?
Yeah, so the whole idea, okay, so once you write the symbol G, you already are talking about any hypothesis, because by definition, G is the final hypothesis, and your algorithm is allowed to pick any small h from the hypothesis set and call it G. Therefore, when I say G, don't look at a fixed hypothesis. Look at an entire learning process that went through the script H, the set of hypotheses, according to the data and according to the learning rule, and went through and ended up with one that is declared the right one, and now we call this G. So the answer is patently yes. G can be different, patently yes, just by the notation that I am using.
Some confusion. So with the perceptron algorithm or any linear algorithm, so there's a confusion that at each step there's a hypothesis, but
correct. But these are sort of hidden process for us. As far as the analysis I mentioned, you get the data, the algorithm does something magic, and ends up with a final hypothesis. In the course of doing that, it will obviously be visiting lots of hypotheses. So the abstraction of having just the sample sitting there and eyeballing them and picking the one that happens to be green is an abstraction. In reality, these guys happen in a space, and you are moving from one hypothesis to another by moving some parameters. And in the course of doing that, including in the perceptron learning algorithm, you are moving from one hypothesis to another. But I'm not accounting for that because I haven't found my final hypothesis yet. When you find the final hypothesis, you call it G. On the other hand, because I use the union bound, I use the worst case scenario, the generalization bound applies to every single hypothesis you visited or you didn't visit. Because what I did to get the bound of deviation between in-sample and out-of-sample is that I consider that all the hypotheses simultaneously behave from in-sample to out-of-sample closely according to your epsilon criteria. And that obviously guarantees that whichever one you end up with will be fine. Okay? But obviously it could be an overkill. And among the sort of the side effects, the positive side effects of that is that even the intermediate values have good generalization. Not that we look at it or consider it, but just to answer the question.
So a question about the punchline. So they say that they don't understand exactly how the Hefding works proof shows that learning is feasible. So
okay, the Hefding shows that verification is feasible. Okay, the presidential poll makes sense. That if you have a sample and you have one question to ask and you see how the question is answered in the sample, then there is a reason to believe that the answer in the general population or in the big bin will be close to the answer you got in sample. Okay, so that's the verification. In order to move from verification to learning, you need to be able to make that statement simultaneously on a number of these guys, and that's why we had the modified Hefding inequality at the end, okay, which is this one, that has the red M in it. This is no longer the plain vanilla Hefding inequality. We'll still call it Hefding, but it basically deals with a situation where you have M of these guys simultaneously, and you want to guarantee that all of them are behaving well. Under those conditions, this is the probability that the guarantee can give, and the probability obviously is looser than it used to be. So the probability of bad thing happens when you have many possibilities is bigger than the probability that bad things happen when you have one of them. And this is the case where you added up as if they happen disjointly, as I mentioned before.
Can it be said that the bin corresponds to the entire population in us?
The bin corresponds to the entire population before coloring. So remember the gray bin? I have it somewhere. We had a view graph where the bin had gray marbles. So this is my way of saying this is the generic input, and we call it script X, and this is indeed the input space in this case, or the general population, okay? Now, we start coloring it according when you give me a hypothesis. So now there is more in the process than just the input space. But indeed, the bin can correspond to the general population, and the sample will correspond to the people you polled over the phone, in the case of the presidential thing.
Is there a relation between the Hebding inequality and the p-values in statistics?
Yes, there are, I mean, so the area where you are trying to say that if I have a sample and I get an estimate on the sample, the estimate is reliable, the estimate is close to the out of sample, the probability that you will deviate is a huge body of work, okay? And the p-value in statistics is one approach, and there are other laws of large numbers that come with it, okay? I don't want to venture too much into that. I basically picked from that jungle of mathematics the single most useful formula that will get me home when I talk about the theory of generalization. And I want to focus on it, want to understand it in this specific formula perfectly. So when we keep modifying it until we get to the VC dimension, things are clear. And obviously, if you get curious about the law of large numbers and the different manifestations of in-sample being close to out-of-sample and probabilities of error, that is a very fertile ground and very useful ground to study. But it is not a core subject of the course. The subject is only borrowing one piece as a utility to get what it wants. Okay, so that ends the question here. So let's call it a day, and we will see you next week.